Welcome back to ch205. In this video, I'll be talking about section 9.3 of the textbook, nonlinear programming. In the last video, we talked about linear programming, where the objective function as well as constraints were a linear function of the variables. Now, in this section, nonlinear programming, we're going to look at problems where either the objective function, the constraints, or both are nonlinear function of the variables. So as an example, we'll look at example 9.3 of the textbook. It's a pure mathematical problem at this point. I think there is not any engineering interpretation for this problem. Let's say we want to minimize an objective function like this, which is function of x1, x2, x3, subject to three constraints where x1 plus x2 plus x3 is constant, x1 squared plus 5 times x2 is also constant, and the non-negativity constraints where we had for linear programming as well. So let's say how we're going to minimize this using these three constraints using spreadsheet or the solver. Okay, so I'm going to just quickly jump into the spreadsheet. So here's the spreadsheet version of the problem. And if I make this a bit smaller, then you would see the problem over here, as well as the solution. Okay, so we're going to set up three cells for x1, x2, and x3. We're going to start with guess values. Let's say 1, 1, 1. And I'm going to formulate the objective function into this cell. It's supposed to be 2 times x1 squared plus 2 times x2 squared plus x3 squared minus 2x1 x2 minus 4x1 and minus 6x2. That's exactly right here. Okay, so this is going to be our objective function. Constraints, we have two constraints. Let me just expand this a little bit. So this is the left-hand side of the first constraint, which is x1 plus x2 plus x3, and the right-hand side is 2. I just have it on this column, column D. The second constraints, x1 squared plus 5x2, that's equal to 5, and that's identical to this constraint. And the non-negativity constraints come in the solver window. We don't have them here. And just to summarize the problem, I have just the constraints as well as the objective function right here. Okay, so let's solve this problem. I'm going to go to Data, and then Solver. So the objective function is going to be this cell, which is B3. It's a minimization function, right? So we're going to minimize this problem. This is the minimization. We want to minimize the objective function. Okay, the variables are from this cell to this cell, which is A2 to C2, and then the constraints are B4 is equal to D4. So here's B4 is equal to D4, and then B6 is equal to D6. B5 is equal to D5. That's all about it. And make sure you click on GRG nonlinear, not simplex LP. This is nonlinear programming. And then for timing, you can maybe say 100 seconds and maybe 100 iterations maximum. And this also should be some number. You're going to leave this blank. Okay, so say OK here. And then we're ready to solve. So we're going to click on Solve. And you see that the initial guess has changed to this, and that's the solution. It says the solution found. And we want to keep the solution, so we're going to hit OK. This is it. And that's how we can solve a nonlinear programming using spreadsheet. Okay, so the next example we're going to look at is a bit more complicated, and that's example 9.4. We have a reactor. It's called continuous stirred tank reactor, where we have reactant A, which reacts to 2B, also reacts to C. We have the forward as well as forward-backward reaction rate. And the third reaction is reactant B produces D and C. Okay, and the reaction rates are given, R1 through R4. And we also have the relation between the reaction rate and reaction or rate constants. So reaction 1, the rate of reaction 1 is equal to the K1 times the concentration of 1, or concentration of A, and so forth. So these are the rate, and K's are the rate constants, all are given. We want to write the equations to solve for the concentration at equilibrium. So how we can write this? Well, we look at every equation and write the corresponding reaction for each. Because for the first one, it says A goes to 2B, so the reaction would look something like this. The concentration of A is equal to initial concentration of A plus the volume divided by Q. So this volume divided by Q gives the total time, because the dimension of this is V, dimension of this is volume per time. So V times Q gives you the time dimension. In other words, this is nothing but writing the reaction for the first two actually reactions. So if you want to really write this in a mathematical form, then it has to be similar to what we did with differential equations. And in fact, this is a differential equation, but the book actually pretends that to be like a finite difference. But we can start with differential equation first and then write the finite difference and then try to solve the finite difference version. So we're going to have dA dt is going to be equal to minus R1. Let me just make sure. Yes, minus R1, because R1 is removing A and converts them to B, so it has to be minus. That means that the concentration of A is going to go down because of R1. And then minus R2. So here minus R2. And then plus R3. So that's all about it. This is just the concentration of A. For concentration of B, you can write the same thing. You can say dB dt is equal to R2 plus, because R2 is adding concentration of B. Just make sure let me see, that is R1, right? And okay, so that should be 2R1 because the concentration gets doubled. So this should be, actually it should be 2 times R1, because R1 is adding concentration of B, and that's going to be double because the coefficient here is 2. And then what else? So concentration of B is going to go down because of R4, so it's going to be minus R4. And then the same thing, dC dt is equal to, the concentration of C is going to go up because of R2, so it's going to be R2 minus R3 because R3 removes C, and then R4. Okay, so let's write down the first equation to find a difference version. So the first equation is going to be A minus A naught, so that's the final difference, right? The future concentration minus current concentration is the initial concentration, divided by the time. So the time is going to be V divided by Q. This is just what I said. The volume divided by Q has a dimension of time. So this is delta A, the change in concentration of A divided by the change in time, is equal to minus R1 minus R2 plus R3. Okay, so let's compare our first equation, well, last equation here with what's given there. So let me actually move this block. So I'm going to move it down. So you'll see what's going on. Let me see, can I go down? Further down. I cannot move it actually, I'm sorry. I can move it to the next page. That's bad about Mac, but anyways, that's what it is. So let's move it back up. Okay. So, well, anyways, so let's check this one. So it's going to be A minus A naught divided by V over Q equals minus R1, which is minus K1 CA. And that's what it is. So this is CA minus CA naught. And then you can divide through by V divided by Q. So far so good. The right hand side is going to be minus K1CA. I mean, that's the leftover if you do the simplification. So here's minus K1CA right here. And then R2 is going to be K2CA to the third half, or 3/2. And then here is minus K2CA to the 3/2. Okay, and then the last one is plus R3, which is K3 times CC squared, and here's plus K3 times CC squared. You can go ahead with the same approach and convert the second one to the final difference. It's going to be 2R1 minus R4. On the right side, 2R1 is going to be 2K1CA. So here's 2K1CA minus R4, which is K4CB squared. And the last one, which is DC dt, is going to be R2 minus R3 plus R4. So minus R2 is going to be minus K2. Let me make sure. So it's going to be plus R2, right? So it's going to be plus R2 minus R3 plus R4. So minus R2, I'm sorry, plus R2 is going to be K2CA C to the 3/2. Minus R3 is going to be K3CC squared. And then plus R4 is going to be K4CB squared. So this is also true. And then the last one I forgot. You can say dt is equal to R4, because R4 generates D. There's no D here, there's no D here, that's it. So that's going to be CD minus CD naught divided by V divided by Q, and everything is equal to R4, which is K4CB squared. So now we have 4 equations here. We know all the K's. And the question is, what is the concentration? So we're gonna solve for CA, CB, CC, CD, given we know the initial concentrations, we know the V, we know the Q, we know the K's, right? So these are the K's. And let's see, we need V and Q. Is that given? Yes. Well, we know CA naught. We know the volume rate, this is Q. We know the volume, which is 100. And all others are 0. So CB naught, CC naught, and CD naught all are 0. Okay, so let's look at how we can solve this problem using the package. Using the solver. So I'm going to exit this and look at example 9.4. So let's expand this. I'm going to increase the font a little bit to 14 and make this 125% so you guys can see, and then no border lines. Okay, so we have the K's here, V is given, Q is given, the initial concentration, exactly like the problem says. And now let's see how we can set up the equations. So we need to write the objective function as well as the constraint. So in the next video, I'll show you how to write these, the objective functions as well as the constraints, and how we can use solver. So stay tuned for the next section on solving example 9.4 of the textbook.